Hi everyone, welcome to another weekly ZX seminar. Today we will have Razin Shaikh, who will be talking about the Focked-up ZX calculus, or how to picture a continuous variable of quantum computation. Please, Razin. Right.
Thanks. Yeah, this is joint work with Leah Gay and Stefano Gogioso. Okay, so I'll start by giving some background and motivation, and then I'll introduce the calculus, um, describe its generators, rules, and gates. I'll talk about Gaussian completeness and some applications. So yeah, let's start with some motivation. Uh, why should we care about continuous variable quantum computing? Well, so first of all, because we are working with continuous variables, we can simulate um, physics, which is natively continuous variable. So this includes bosonic systems and various quantum field theories. So having continuous variable quantum computers allow us to perform native simulation rather than encoding something like continuous variables in qubits. But the most interesting reason for continuous variable quantum computing is quantum error correction. So with this, a lot of hardware natively has this quantum harmonic oscillators, which has continuous degrees of freedom. And if you want to fully utilize the redundancy in your hardware, you might want to develop codes which encode your qubit quantum computation in this infinite dimensional Hilbert space. So you can fully utilize the most redundancy that's available to you. And um, and this framework is already supported on various hardware. So it's not just photonics, which is the most common one, but continuous variable quantum computing is also possible. And there have been experimental demonstrations for superconducting in trapped ions hardware. So what is CVQC? What is continuous variable quantum computing? So we all know that a single qubit is a two-dimensional quantum system, and you can represent the state of that system with a superposition of ket0 and ket1. And when you generalize this to qubits, you get a d-dimensional system, and your arbitrary state is a superposition of d of your basis states. Now, when you generalize to infinite dimensions, you get a Q mode, and the Hilbert space there is L2 of R. And there are two ways you can write the most general state. The first one is you consider the continuous degrees of freedom. So you get ket x as your basis state, where x is a real number. And then you consider a wave function over that. So your one QMO state would be a wave function psi of x over your basis states ket x. Alternatively, you can have discrete infinity, where your basis states are these Fock states that that take values in natural numbers. So these Fock states go from 0 to infinity, and they are natural numbers, and you can describe a state here like that. So this is closer to like QDIS, which is also discrete.
Razin, if I can interrupt you here. So the thing you've written there with this integral over like position eigenbasis, this is just like some nice syntactic sugar, right? The real elements of the Hilbert space are functions themselves.
Mm-hmm.
Okay.
Yeah.
And then this is your interpretation of like what this function means. But, yeah.
Yeah.
Okay.
Okay. Um, so yeah, in the infinite dimensional case, we get three different kinds of orthogonal bases. So in the qubit and qubit case, you usually have two complementary bases: your computational basis and your the Fourier basis. But for infinite dimensions, there are three natural choice of bases that you can have. So first is your position basis, where your ket x takes values in real numbers, and then there is the momentum basis. So position and momentum are the complementary basis here, but you also have the Fock basis, which is the discrete basis, which corresponds to, let's say, the number of photons in your system. And these three bases are related to each other in this way. So you have the position and momentum bases related to each other by the Fourier transform. But then you also have the position and the Fock bases, and you can go between them using this thing called the Hermite transform. And the Fock and momentum bases are the same. So you have a Hermite transform, but you also need to apply a diagonal unitary. Now, so like an example of Hermite transform is you can represent the ket n basis state as this integral, where you have this integral and you're integrating over this Hermite polynomials. And these Hermite polynomials are really complicated. Like they're not the easiest to work with. And that also motivates us why we may want to have a nice graphical language to deal with this sort of calculations instead of working with these Hermite polynomials more directly. So, okay, so let's start by introducing this graphical calculus. So as the generators, we have, first of all, the Z spider. So in the qubit case, or in the qubit case, the Z spider matches the computational basis. So if you input ket x in one of the wires, it makes sure that all of the other wires are also ket x. So similarly, in the continuous variable case, the Z spider matches the position basis state. So you have x and x that are matched. And along with that, we can also have a label on the Z spider, let's say f, and you can specify the coefficient of your integrals. So a function, this f goes from real numbers to complex numbers, and you add f of x as the coefficient of the x basis state. We also have the Fock spider, and this again does the matching of the basis states, but now for the Fock basis. And again, we can label the Fock spider with a function that goes from natural number to complex numbers, which specify the coefficient. And as the last generator, we'll also allow global scalars to be freely floating in our diagrams, just for convenience. Now, using just the Z spider and the Fock spider, we can define the X spider as a notation. So the Fock spider diagonalizes the Fourier transform. So this minus I to the n is the Fourier transform in the Fock basis. So using that, we can put the Fourier transform around the Z spider to obtain the X spider. And the X spider matches the momentum basis and applies the coefficient for f of p. And yeah, throughout this talk, if I have a unlabeled Z spider or unlabeled spiders, I just mean a constant function labeled 1. So we'll omit the labels in that case. Now, using this spiders, we can describe the basis state that I mentioned before. So I can label the X spider with this function, e to the minus I to pi px, and this function corresponds to the basis state ket x. So a state diagram with one output is ket x here. And similarly, I can have ket p using the Z spider. And for the Fock basis, I can just label the Fock spider with the Kronecker delta function delta n, and that gives me ket n. Okay, some more notation. We can define this multiplier. So multiplier is this arrow with m labeled in real numbers. It's defined like this, but what it does is if I input ket x, it multiplies by m. So for input x, it gives me state mx. So that's why it's called a multiplier. Now, the last thing for notations is that we can define the W node. So in the qubit and the qubit case, we have the ZX calculus, the W calculus, and this W calculus, the W node is the generator that's used in the ZW calculus. So here's how it's defined. But what it does is if I input Fock states N1 to Nk, it gives me the output, which is the sum of all the N1 to Nk basis states. So if I input, let's say, N1 to Nk photons over here, it puts all of those photons into a single wire. So it sums those basis states. And you also have this coefficient in front, which is necessary for various reasons, including the fact that you need this to make the bialgebra happen. So, okay, these are the rules. These are the generators and notations that we are going to use. And here are the rules of
Razin,
the
could I ask a quick question about the W spider?
Yeah.
So it looks like your W spider is related to the X spider via just local operations here. Is that right? So that would be kind of quite different to the qubit case.
Um, well, yeah, from the qubit case, yes, but also it's not that different because in the qubit case, at least in the mixed dimensional ZX, the X spider and the W spider can be converted to each other. Because the main intuition is that X spider does addition modulo D and the W does just addition.
Okay, right. Yeah, I guess so the qubits are the one that are special. It's yeah.
Yeah.
Okay, thanks.
But also this is not just X spider surrounded by stuff because we have this 2 to the n over 2 spider, which is in the Fock basis. So what this does is pretty non-trivial.
Yeah, but I mean in qubits, like no matter what like invertible matrix you apply to your qubits, you're never going to be able to convert an X spider into a W, right?
Yeah.
Yeah. Okay, thanks.
Okay, so here are the rules. So first we have the fusion. So in the continuous variable case, if you apply fusion between two Z spiders, you need to multiply the functions pointwise. So if you have F1, F2, it becomes F1 times F2 pointwise multiplication of the functions. And same thing for the Fock basis fusion, the Fock spider fusion, and there's also fusion for the W node. And we have the copy rule, which just copies the basis states. And we have three different bialgebras. So we have the ZX bialgebra, we have the Fock-W bialgebra, and we have the WW bialgebra. So there are three bialgebras in this calculus. And yeah, and this is just saying one input, one output is identity. More rules. So the first rule here is the Fourier transform rule, which says that if I have a state which is written in the Z spider, then for any such state, I can convert it to a state in the state with the X spider by applying the Fourier transform of the inner function. So for states, just one output Z or X spider, they are equivalent by Fourier transform of the inside function. And very similarly, I can convert from the Z spider to the Fock spider, but now I'm applying this this transformation, which is the Hermite transform. Yeah, and also this works backwards. So if I can go from the X spider to Z spider by applying the inverse Fourier transform, and the Fock spider to the Z spider by applying the inverse Hermite transform. And here are some rules for the multipliers and the scalar. Next rule is the Euler decomposition of the rotation. So if I have a rotation, e to the I theta, it can be represented as green, red, green. And next is the beam splitter rule, which says that there are two equivalent ways of writing the beam splitter. Or in other words, if you have two matrices that are orthogonal, then writing them with the W Fock spider or with the ZX and multiplier, they're equivalent. And the last rule is the most fun because it looks like a triforce. So it says that if you have three W's that are connected to each other, that's equivalent to a Z spider. And perhaps this is the most unintuitive because to prove this, we had to use Hermite Hermite polynomials product formula from like 100 years ago, which was quite exciting. Okay, so now using this, we can represent some common operators and gates. So first of all, we have creation and annihilation operators. So if I take the W and input ket1, so one of its leg, then it acts as a creation operator for the harmonic oscillators. It sends ket n to n+1, and there's the annihilation operator. We also have the quadrature operators, which says that if I input ket, it tells me the position value of the input. So if I input ket x, it gives me x times ket x. And this is the momentum version of the quadrature operator. And we also have the number operator, which is just a Fock spider labeled n. Now we also have the Pauli's, or as they're called in CV, the Heisenberg-Weil operators, which can be represented like this with the character functions. And now we can describe some common gates. So we have the displacement, which is just applying to shifts in position and momentum. We have squeezing, which happens to be just the multiplier, and rotation, which is a Fock spider labeled e to the I theta. And for the two-mode Gaussian gates, so sorry, yeah, these were the Gaussian gates, which are like, so Gaussian is like the Clifford version, it's like the stabilizer for CV. We also have two-mode gates, which is the C0, control phase, and beam splitter. And there are two equivalent ways of writing the beam splitter. Now, apart from the Gaussian gates, we also need some non-Gaussian resource to make this approximately universal, for which we can choose like a cubic gate, a cubic phase gate, a Kerr gate, or this entangling cross-Kerr gate. All right, so next, let's look at the completeness for the Gaussian part. So the stuff which does not involve the non-Gaussian things. So how is the Gaussian fragment defined? It's all the diagrams generated by these Z and X spiders. So the Z spider here is labeled by e to the I by ax plus bx squared. So here we have a linear component in the exponent and a quadratic component. So we cannot have anything apart from these labels. So here a and b are real numbers. And similarly, we have this linear and quadratic component for the X spider. And finally, we have delta 0, which is the vacuum state. So let's say the canonical Gaussian state, and all the other Gaussian states can be obtained by applying these Z and X spiders to vacuum. And we show that this fragment is complete, which means if you have two diagrams that are in the Gaussian fragment, which are constructed using these generators, and they have the same semantics, so they correspond to the same linear map, then we can prove that they are equal using the rules of the calculus. And to prove this, we do this by translating another completeness result. So this paper by Booth, Carrot, and Comfort, they define this calculus called the graphical symplectic algebra. So this corresponds to the Gaussian fragment of CV. And their semantics is given in terms of these affine Lagrangian relations. And we use completeness to this calculus to show that our calculus is complete. So first thing, and here are the rules of their calculus. So the first thing we need to do is we need to show that all the generators are convertible, are translatable back and forth. So there's an invertible translation between them, which is quite straightforward. And we also need to show that all of the rules in their calculus are derivable using our rules, which is what this proposition is proving. There are some more technicalities about like how you can make the semantics work, but I won't really go into that right now. Okay, yeah, and with that we get the completeness for the Gaussian fragment. Okay, any questions so far?
Maybe this is something for the end of the talk, but the Triforce rule, how does this, is this something you sort of discovered you needed when you did this completeness translation? or is this here for some other reason?
No, it's well, it's not something required for completeness. I'm not sure where we needed it, but I think so this is useful in many places, but I think we were just trying to see what this like ancient Hermite polynomial product formula translates to in our calculus, because just mainly out of curiosity, and then we found that it has a very nice form. But we actually use it in several places. Oh, I think Neil has a hand up.
Yeah, I just wanted to remark that it does seem as though that Z spider would, it's an analogon to something that would be in the stabilizer fragment if you were dealing with finite dimensions. So I would rather expect the stabilizer fragment, I think, is analogous to the Gaussian fragment of this calculus. So I think you would need it for completeness. That's speculating on my part.
I mean, it is possible, but because we were doing it by translation, we didn't really need to use the triforce rule there.
Does something like that hold in the qubit counterpart, where like you take a triangle of W's?
Yes, it also holds in qubits actually. So where
Okay.
if you take three of these like W nodes, that corresponds to the X spider in the qubit case, and it also holds in qubit case. And in fact, you can show that if you consider this arrangement of like any monoid that's any monoid that's whose comonoid is its transpose, then you can show that you can always get a Frobenius algebra with this. Because I didn't show the general version here, but like so any monoid that's has bialgebra with itself, which this W does, you can apply the bialgebra and reduce it to a normal form, and you can show that it satisfies all of the Frobenius equations. So this actually works for in any dimension, or even more generally.
It reminds me of this characterization of the W node in the qubit ZX, where if I take a triangle of, I think, X spiders, which are connected by like a Z spider on the wire in between them, which is a pivot three phase, I get like a triangle of spiders, and this forms a W node. I think it's in the Dodo book, like this characterization of W.
Mhm.
So that's
And
like
I mean,
also a triforce to get a W, but here just the other way around.
and yeah, and also like in the qubit case, you get also the other one, which is if you take three W nodes and connect it like a triangle, then you get the X spider. So I think that makes sense because you can go from Z to X, sorry, X to W and W to X in the qubit case in the same sort of diagram.
Thanks.
Okay, so now let's look at some applications of this calculus. So first, I'll talk about quantum error correction. So a very common or the most popular proposal for error correction with continuous variable is the GKP code. So here you want to encode your qubit states in this oscillator. And the way you do it is that you consider periodic basis states. So you consider Dirac deltas. You consider a comb of Dirac deltas that are each separated by 2 square root of pi distance. So ket 0, logical ket 0 would be a comb of Dirac deltas, which is just infinite Dirac deltas that are separated by 2 square root of pi. And for ket 1, you would consider the same comb, but now it's shifted by square root of pi. So, or in other words, ket 0 is all the even multiples of square root of pi in the position basis, and ket 1 is all the odd multiples of square root of pi in the position basis. And to represent this in the calculus, it's quite straightforward because we allow arbitrary functions on the Z spider. We can simply label them by the appropriate functions. So writing the state, here's how we'll write it. We'll say 0L1L, where it represents the appropriate wave function. Now, this this infinite superposition of Dirac deltas is actually not physically realizable. So in practice, what people are interested in is the finite squeezing case, where instead of considering perfect Dirac deltas, you approximate them by Gaussians that are that have some finite width. And you also consider a Gaussian envelope, which suppresses the Gaussians that are far apart. So it does not. So this gives you a state which you can construct in the lab with finite energy. And the 0 and 1 are again still separated by square root of pi distance, so they're still shifted. But with ZX, you get a very nice perspective on this because you can show that these finite squeezing GKP states are actually just same as the ideal ones with some transformation. And this transformation is actually exactly the Gaussian regular. It's actually the same as like the Gaussian noise that you're adding, the Gaussian regularization. And to see that, you can see that you have this vacuum state, which is a Gaussian state, which you can squeeze using this parameter, which is the width of your Gaussian, and then you inject this this so-called this Gaussian regularization in the Z bases, and also you need to do the same in the X bases because the GKP code is symmetric with respect to the bases. So yeah, with this diagram, you get a very nice picture of what this approximate squeezing is. Now, we can also describe an encoder for this code by noting that if I have a 0L, get 0 GKP state, and if I apply a shift in the position basis by square root of pi, I get 1. And we can use this fact to apply to this diagram. So if I input ket 0 to the multiplier square root of pi, I still get ket 0, and I just get the identity over here, which is the logical 0 state. But if I input ket 1, then that will make it chi sub square root of pi, and that will shift the ket 0 to become ket 1. Now, we can actually define this mixed dimensional Z spider, which is taking from the mixed dimensional ZX calculus and generalizing it to infinite case, where you canonically map ket 0 and ket 1 to ket 0 and ket 1 in the position basis. So this is an arbitrary choice, but it's a very nice one because this corresponds to your encoder now, and you get some nice rules with this mixed dimensional Z spider as well. We can also describe a syndrome measurement circuit. So here's what it looks like. So first of all, this state that I have here, it's same as the plus state in the logical in the GKP encoding, but I'm writing it as like p mod 2 square root of pi equals 0, the indicator function for that, because it's easier in calculation. So you start with the ancilla, which is your ket plus logical. You apply a C naught, and then you perform this homodyne measurement, and the output of the measurement is S. And you can see that this actually does detect the error. So if you have a state in your logical subspace, psi, and an error happens, let's say a shift by chi sub epsilon, then you can show that this, after some rewrites, you can show that this error is same as your measurement output S modulo square root of pi. So what this means is that you're measuring the error modulo square root of pi. And if you assume that your error is not too big, so it's not greater than square root of pi, then you can apply a correction of minus S mod square root of pi to correct for this error. So this is how the error, like the syndrome measurement and correction happens in the GKP code. Okay. So the next application we looked at in of this calculus is Gaussian boson sampling. So this is a non-universal model of quantum computing. And a lot of interest. There's been a lot of interest in this problem because you can prove that it samples from a Sharpie hard distribution, and there have been several demonstrations of quantum advantage using Gaussian boson sampling. And what we do in this paper is we prove that Gaussian boson sampling is hard, just using diagrams. And the reason why Gaussian boson sampling is a hard problem is because it samples from a Hafnian of a matrix. And this Hafnian function is a function that takes in a matrix and gives a number. And this is you can show that calculating the Hafnian is Sharpie hard. And the amplitude for of this, which is like, you start with psi, which is some Gaussian state that you have generated, and then you sample n1 to ns number of photons. And this amplitude depends on the matrix of the interferometer that you use to create the Gaussian state, as well as the squeezing parameters. Now, this Hafnian has a very nice relationship with the perfect matchings of the graph. So a perfect matching is, if you're given a graph, a perfect matching is, give me a set of edges such that all the vertices appear only once. And the set of all such perfect matching, the sum of all such perfect matchings is actually the Hafnian, where the matrix was your adjacency matrix. And this also generalizes to the weighted graph case. Now, in the ZX calculus, we have a very nice way of representing this perfect matchings. So if you take any graph, you can translate it to the to the ZX calculus using the translation where you replace all the vertices with the W nodes that are post-selected on ket1. So if you have this bialgebra-like graph here, you can replace all the nodes with this W with the ket1 input, and this diagram corresponds to the sum of perfect matchings. So here you can see that it's there are two perfect matchings, so you get 1 + 1, which is equal to 2. And this follows because by inputting ket1 in the W, you are picking a path where the ket1 goes. And this also works for the weighted case. So if I have a weighted graph, it gives me the sum of the weighted perfect matchings. And in general, if I have an adjacency matrix that's describing the connectivity of these W nodes here, A, then this diagram corresponds to the Hafnian of A. So now the goal for showing that Gaussian boson sampling is sampling from a Hafnian is to show that any Gaussian boson sampling circuit can be written in this form, where you have a bunch of W's and some adjacency matrix describing its connectivity that's post-selected on the measurements. So to do that, we start with looking at what the Gaussian boson sampling circuit is. So here's an example. And now, in this circuit, we start with vacuum states, and you apply some squeezing to it, which has some parameters. And then you have rest of it, which is the which is combined, which is called an interferometer. You apply this interferometer, and then you perform the photon number measurement. Now, it's already known in the literature that this interferometer part can be written as this diagram, where you have a bunch of W's and you have a bi-adjacency matrix, let's say U, that describes the connectivity, where U is called the interferometer matrix. So then we start with the normal form then we want to derive a normal form for Gaussian boson sampling, where we also input the vacuum state and a bunch of squeezing with some parameters. And we want to reduce it to a form that we like. And so yeah, we do that, and we show that this diagram can be converted to this diagram where you have a bunch of W's, and there's the adjacency matrix, which is given here, that describes its connectivity. So this is the normal form for any Gaussian boson sampling circuit. And with this, now we just need to show, now we just need to like show what it samples from. And for that, you just input the, or just post select on the measurement outcome in the Fock basis. And you see that that's same as the Hafnian of this matrix. Technically, based on what the measurement outcome is, this matrix changes into something called a submatrix. But yeah, that's not very difficult to like modify here, and we show that in the paper. So yeah, with this we can apply just diagrammatic manipulations to show that Gaussian boson sampling samples from a Hafnian, which is sharply hard. Yeah, any questions about QEC or GBS?
Yes. Let's see how I want to phrase this. So these calculations you do where you reduce to this normal form that shows how the Hafnian is sort of comes into play here. Are you essentially doing the types of calculations that the people have done to originally derive this this equivalence, but then just graphically, or is this like if you were to translate this back into sort of symbolic reasoning, like really a different kind of proof than they had?
I think it's different because like we don't, I'm not sure because I've not like I'm not sure, but I think it's very different because you're starting with this diagram and you're just showing how the diagram changes, and you end up with a final diagram that looks like this. So I'm not sure how it would be the same. Like I don't see how it would connect to the I don't know how this would tell you that this is same as the sampling from the Hafnian.
Leah has raised her hand. I think she has an opinion on this.
I get that the big steps, the main steps are matching up. Because we also in the literature, proofs of Gaussian boson sampling, you also have the submatrices, and you have this relation, this rule of the squeezing of the vacuum state gives this hyperbolic tangent factors. So we did consult the literature on how to do these proofs. I think that each step, what the big difference is that this being entirely a graph-based proof. So the way we arrive at each of the steps along the way is different because it's all graph rewrites. So that's where we had to apply different techniques.
Thanks.
Yeah. Okay. So to conclude, we generalize ZX to infinite dimensions, and this has continuous and discrete picture all in one. And we also show how those two different pictures interact in a very nice way. And this calculus is also complete for the Gaussian fragment. And we applied the calculus to study quantum error correction with the GKP code and give a fully graphical proof of Gaussian bosons, of the hardness of Gaussian boson sampling. And for future work, so the natural thing to do now is that now that we have ZX calculus, in this case, we would like to give, we should develop or generalize algorithms based on ZX for compiling and circuit optimization, classical simulation, and MBQC. And like some of these things should generalize quite easily from the finite dimensional case, but there will also be some other things that are quite different. So for instance, in MBQC, usually you have this hybrid cluster state where your resource is also built in part of your cluster state, and like the way it behaves there is quite different. Now for this calculus, it would be good to prove more completeness. So in the Gaussian boson sampling proof, what we showed that a large class of Gaussian diagrams can be which is represented in this like Fock-W language can be reduced to a normal form. So it'd be very good if we can describe a Gaussian fragment using just the Fock-W part and prove a Gaussian completeness result there. And yeah, so recently with Titwan and Cole, we have started like looking into that. And it would also be cool to prove completeness for the approximately universal fragment, because you would probably need that for, you need that for universal quantum computing. I think beyond the approximately universal fragment, proving for the complete universal fragment would be probably very difficult, if not impossible. But yeah, because I'm not sure even how you would define the semantics in that case. And finally, more quantum error correction. So one thing that's interesting here is how we can define Pauli webs and some of this, how we can generalize some of the error correction procedure that have been done in like the qubit case. So yeah, we have recently been looking into Pauli webs, how we can like perform fluctuation for the GKP code. But other than that, we also want to look at what the multimode GKP code looks like. So here, the example I gave was when one qubit was encoded into one Q mode. But it's also interesting to look at what happens when you encode one qubit into multiple Q modes, or when you encode or when you concatenate the GKP code with a outer qubit code. And this is a very common proposal for QEC with continuous variable systems. And finally, it would be good to look at other types of codes, which include CAD codes and binomial codes, and also dual rail codes. Yeah, that's all I had to say. Thank you.
All right, thank you, Razin, for the very nice talk. People can use the clapping emoji to applaud our speaker. Do we have any questions from the audience? Okay, I will go first. So a completeness proof that has worked very nicely for sort of the QDIT case for the stabilized ZX is to prove the spider removing versions of local complementation and pivoting, and then show that you can remove all internal spiders, and in that way you get a normal form. Does that work in a Gaussian fragment?
Sorry, can you repeat like what's the proof again?
Yeah, so the proof strategy is you prove a version of local complementation and pivoting that each remove a spider, and then you just keep applying these rules until all internal spiders are removed, and then your normal form consists only of boundary spiders, and then yeah, that is enough to get completeness.
Yeah, so Cole has said in the chat that
Yeah.
that is their proof.
Okay.
So by translation, that is, yeah.
Yeah.
Also, that's what happens for us.
So this is just a question based on my confusion about how to think about these infinite dimensional things. But you have what looks to me like you have a continuously infinite dimensional basis, but you also have a discrete infinite dimensional basis, namely the Fock states versus the momentum or position states. This is a vague question, but how does that work? How are both these things like bases for this thing?
Well, so the actual proper basis is the discrete one, but because like you can go between discrete and continuous bases using the Hermite polynomials. So in the even in the continuous case, your actual basis is the basis given by these Hermite polynomials. So these Hermite polynomials are a family of orthogonal or orthonormal polynomials, and that's the basis of L2 of R. But the continuous basis ket x that I've written here is actually very useful in in working with these sort of things, but they correspond to states that are not normalizable. So like so to give you like proper semantics, we need to like we need to work with non-standard analysis. So that's how we are giving semantics for these ket x, which are position and momentum basis states. But if you're just working in L2 of R, then ket x won't be the actual real basis. But for us, it is.
Okay, do we have any other questions from the audience?
So this isn't the normal like Fox like this isn't the same the same standard construction of the Fock space because there's some non-standard thing going on. Like it's
Oh,
not just L2 of the Hilbert space completion of the symmetric. Yeah, it's not the Hilbert space completion of the symmetric algebra or
so maybe I should say that like so far what I've presented like is like the standard way of doing things because I've like kind of not mentioned any non-standard intricacies here.
Michael, you want to ask a question?
Yeah, and I just wanted to confirm one point, which was with the calculations with the Hafnian. It seems like that basically didn't really require the full, how do I want to say this? In terms of sort of the story being laid out, the full calculus here of XP and Fock space. It seems like with the Hafnian side of things, it really only used the Fock space side of things, and thus in some sense doesn't need the sort of the full breadth of the formalism for that.
So I think so for most of it that's correct, but I think there is one main difference, which is sorry, let me get to this slides. Is the squeezing part. So here you have the vacuum and the interferometer, that's all just Fock space. But once you apply squeezing, that's not very straightforward because the way these like multipliers, the squeezing x
Yeah, I
is
see what you mean.
get x
I see what you mean.
to r times x. And the main part which does not appear here, but is like that requires the also the Z and X spiders is this part to like prove that to prove a form of like a squeezed vacuum. But if you're willing to like just make that an additional axiom, then yeah, then you wouldn't really need to use this.
Yeah. So basically, if you want to sort of do it natively, as it were, you do need to do something. You do need to add something more. It's just how much more you want to do. Okay.
Yeah. But you're right. Like I think the Gaussian boson sampling uses more of the Fock and W, except for the squeezing part. And but at the same time, like the GKP examples are primarily heavy on just the ZX fragment.